My name is Chengpu Wang. Today, I will give you a presentation on new axiom set for two-dimensional Euclidean geometry. It has a subtitle, The Fruit for Reinventing the Wheel. Let's start by discussing the thought process. There are four steps of thinking. First, observation. Second, generalization to abstract observation into definition and axioms. The third is a deduction, which to use logic to turn definition and axiom into theorems. Fourth, applications, to check for the consistency of the theorems and check the theorems in reality or in prediction. In many abstract maths, the reality check and prediction tests are not possible. So the generalization step has to be extremely careful. Let's start a thought experiment. We know Euclidean geometry is a geometry on a flat plane. Instead of asking the detail of the Euclidean geometry, which is part of the deduction, we will concentrate on observation and generalization by asking what flat means. We could also answer this question by some additional assumption, like uniform abstraction, meaning that each point is identical to any other point. By this abstraction, we will compare flat surface versus a spherical surface. This abstraction is commonly used in mathematics. Another thing we notice that flat is a special case of smooth. To understand smooth, we need to come up with a non-smooth surface. Of course, all the rough surfaces are difficult to study. However, we can study a surface which has only one point, one singular point, which is not smooth, and that is a conical surface. Let's come to the purpose of this presentation. You can get knowledge from internet and AP courses. You can sharpen your detection skill by participating in Math Olympiad and other competitions. Here, I'm concerned with the observation and the generalization related thinking, which come into different form. The first one is appending thinking. That means you compare what you are studying with something different. For example, if you want to understand the Euclidean geometry truly, you have to compare it with a non-Euclidean geometry, as we will do in this presentation. And the next one is called critical thinking. You took it not for granted for any standard claim. The third one is called original thinking. That means when you study a new subject, you should cherish all your naive questions and uncertainty, because that may have some truth in it. By the way, it only comes once, right? If you already take something for granted, you lost forever. In fact, this presentation is a result of my daughter Alice, who learned Euclidean geometry for the first time, and all the naive questions she asked, and let me think twice. One of the questions she asked is that how you measure an angle. I started to lecture her. You have an angle here, and you make a circle from the vertex of the angle, and get an arc like this. Then measure the arc length and divide by radius. Then the next question, Alice, is then that how would you measure the length of an arc? Well, the standard answer is you measure the angle and multiply it by the radius here. But that question let me realize the standard answer has a problem, because it's a circular definition between angle measurement and the curve length. And once you find something wrong, you need to have alternative thinking. Now, the question here is it necessary to do alternative thinking, or is it any value for reinventing the wheel? My answer is, before you study something You should try to reinvent the wheel. If the created solution is worse, you will learn something. If the created solution is better, you will invent something. Let's review the existing AMP set for the Euclidean geometry. The original Euclidean set has 4 plus 1 axioms plus 5 rules for general math. It's a birth of modern mathematics and rationalism. It is constructive. It uses straight line, segment, and circle as building block, as what our new axiom set will be. There is also a Hilbert set from the great mathematician David Hilbert. It has 21 axioms in 5 groups. It is a standard answer now. It is descriptive, and it uses straight line and straight triangle as building block. There is also a Birkhoff axiom set, which requires angle measurement as another foundation measurement independent of distance measurement to answer the circular definition between the angle measurement and the curve length. As we know, this is not true in practice, so it is basically a useless set. There is also the metric foundation for a lot of other geometry, like differential geometry. The metric basically means you can measure the distance between any 2 points. Let's analyze the Euclidean axiom set. First axiom, to draw a straight line from any point to any point. The straight line is actually a straight line segment in modern terms, as we will follow. The distance should define before straight. Second, to extend a finished straight line continues in straight line. Straight line from straight line segment, as we will follow. Continuous need further specification. Third, to describe a circle with any center and a radius. It's actually an axiom about distance because you can use circle as a mean to measure distance. The circle has hidden dimension information. That all right angles are equals to another. What does that mean? It's not very clear. At least it is the least used axiom in practice. The parallel postulation. It is not one of the 4 axioms Euclidean listed in the beginning of these elements, and people discover this should be an independent axiom later. It is also the most discussed one, leading to non-Euclidean geometries such as spherical geometry and hyperbolic geometry. Because the Hilbert axiom set is the current standard, let's look at it in the critical way. First, it's too complex with 21 axioms. Well, we know simplicity is beauty. Let's look at detail. The first axiom in the first group. 2 distinct points always completely define a straight line. A straight line as a building block, but without definition. So Hilbert had to describe it in a more verbose form. Any two distinct points of straight line completely determine that line. And upon every straight line, there exists at least 2 points. Well, if we use set-based definition, perhaps we can simplify this as 1 definition rather than 3 axioms. The other one, 3 points not situated in the same straight line always completely determine a plane. Well, in this sentence, it hides 3 new concepts: dimension, flatness, uniqueness of a flat plane. Imagine if we are studying some very abstract math and we find one axiom contains 3 new concepts. How could we understand it? So the desire is to have no new concept in any of the axioms. The reason for Hilbert axiom set is to supplement to Euclidean set. For example, it defines continuity of the straight line, saying between any 2 points on the straight line there must exist a third point. And it also says these 3 point must have ordered sequence, and also define distance congruency, because Euclidean doesn't mean you can only draw a straight line anywhere. It means you can draw it everywhere, etc. As we know, we will see that Hilbert axiom set also contains additional implied assumptions. Now, let's start our new axiom set. As we would indicate before, a geometry object is a set of points. The point is our presumption, which we cannot define, but assume everybody understand what it is. We can use point to create a geometry set. We say we can have an empty set, a set of 2 points. Here we use a capital letter to mean a point. Or we can have a set by a description of the point. Here we just say it's a set of points which have a fixed distance r from a center A. And the space we're talking about is a set of all points. So a point can be in or not in a geometric object. 2, if a geometric object can be equal or not equal in the same way as 2 set would. 2 geometric objects can be intersect each other in the way as 2 set. 2 geometric objects can be union to create a third geometric object. And here there is a special union called orthogonal union. That means when 2 geometry has at most 1 point in common. And we are going to use a real number as mathematics. And we are going to use limit as a proving tool. Namely, we only use this sequence, 1 over 2n. When n equal to 1n approach infinity, it becomes 0. So the first thing, observation, is Euclidean space we're talking about is stable. It's not changing all the time. So we have a first definition called constructed object. A constructed object is a generic geometric object which can be constructed using a predefined step of the deterministic rule. Let's digest it a little bit. The Euclidean axiom set started with the ability to construct a simple geometry object like a straight line segment, which we will simply call segment, or circle. We need to give some kind of abstraction of the original constructed approach. So we come up with this definition of constructed object. We talk about some abstract step of the predefined step of deterministic rules, and we will clarify it later. So the first action say, if the rule for a constructed object runs twice, the same object is created twice. So that means the step of a constructed object is deterministic, and also means the space itself is stable. The second axiom would say Euclidean space is measurable. What it can be measured with? The distance. The distance first is a real value. It is 0 for a same point. It's a positive value for 2 different points. And it is also observed a so-called triangle inequality between 3 points. AB is equal or less than distance AC plus distance CB. The axiom 2 means a distance exists between any 2 points. If we apply the axiom 1 to axiom 2, it says the distance between 2 points is a constant. The third claim is a Euclidean space is continuous. So we first define something called a straight line segment, or simply segment. So as a straight line segment between 2 points A and B is equal to the set of a point P, which satisfy AB equal to AP plus PB. And also, there is a one-to-one correspondence between the point P and the value of distance AP, as shown here. Let's digest this a little bit. So the first thing, we can notice that because this one-to-one correspondence, we can see this, the geometry of the segment AB is isomorphic to a real range between 0 and distance AB, right? The same way as how the real value be continuous, ordered, etc. That would avoid quite a few axioms in the Herbert axiom set. Another digestion is if the point is in AB and AB equal to AC plus CB. If C is not in AB, then AB is less than AC plus CB. So basically, this is a separation of the triangle inequality into two parts. The definition of the segment is actually not the simplest form. We can have a simpler form. Basically, if we have 2 points AB, and if we can find the midpoint on the segment, then we create a set, in this case, n equal to 1. Then we find the midpoint between the midpoint and any end, and we put in that set. Then that is when n equal to 2. So we continue doing that to find the recursive midpoints, and we create a set. And we can prove mathematically this set is equal to the second set AB. What is the advantage of it? Because it's much easier to test our implements. For example, any segment right now on the screen is formed in this way. As we all know, that for 1 centimeter, if you use 64 pixels to construct it, for a naked eye, it will look like a continuous straight line segment. So you don't have to create, real continuous way, right? You can just do as the second set suggested. So the third axiom said there exists at least one straight line segment between any 2 points. If there exists more than one straight line segment between any 2 points, and these two straight line segments must have the same distance, as we know. And also, it says we can tell the difference between two straight line segments. How? The implied assumption is one, distance AB is sufficiently small. The segment is unique. The immediate conclusion is that one, distance AB or distance CD, any of them is a second small, then segment AB and the segment CD, if they have intersection at all, they will intersect at one point only. The next claims, it says, Euclidean space is boundless and smooth. So the axiom 4 is just a statement for this, right? For any segment AB, you can always extend to some point C on the side of A, or sometimes some point D on the side of B. So the first implication, meaning that Euclidean space is boundless. Boundless actually has two meanings. The first meaning is it can be infinite global range, right? That's what we normally understand about Euclidean space. Another understanding, it is you can actually create a Euclidean space in a local region with an open boundary. Here, the 0 is a closed boundary and 1 is an open boundary, right? You can think, right? If you have a region has an open boundary, you can also satisfy the axiom 4. Another meaning of the axiom 4 is the space is smooth. Let's look at the only non-smooth surface we know, the cone surface. If you have a segment with the tip A as one end. You cannot extend beyond that segment. Here, as I showed here, the shortest distance, the shortest path between B and C is not through the point A. So we can use that to extend a segment in one end to create something called ray. Here, the ray AB starts with point A and passing B. Using that, we can clearly see that the ray can also be defined. The same ray can also be defined by the starting point or any other point on the ray. We can extend a straight line segment from both ends and create something called straight line. So here, use the set. We can clearly see any other two points on the straight line can equally define it. That is one of the axiom set, one of the atoms in the Hilbert axiom set. The next thing, since we have distance, we can show Euclidean space is ordered by distance. Here, we define something called a round geometric object, which is a set of points which has a fixed distance called radius from a center called C here. Here we are talking about round object. We did not specify in which dimension it is. It could be a ball, a circle, etc. From the definition, we can see a point could be inside a round object, on the round object, or outside a round object. Then we can compare the relation between two round objects, A and B, with different radius. When these two round objects are close enough, and one could be inside another, as shown here. When they further enough, and they can be outside each other, as shown here. Of course, we can place them in such a way, one thing inside another, but also have intersection point, as shown here. From here, it's very clear that intersection point must be on the straight line connect their center. We can also have the other case. They are outside each other, but also has an intersection point. When we include all this possibility, come the last one. So when the distance between their center are in a range, they intersect each other, and the intersection is not on the straight line connecting those two centers. A Euclidean space can have many dimensions. Here we want to limit to two-dimensional space. We start from the observation that a straight line divides a flat plane into two separate parts. We capture this by defining points C and D to be on the different side of straight line AB if the segment CD and AB has non-empty intersection. Then we define the two-dimensional space of CD on two sides of straight line AB as the set straight line AB plus the set of all points which is on the opposite of AB with C, and the set of all points which are on the opposite of point D with AB. We can define the two-dimensional, two-sided space CD on two sides of straight line AB if the two sides has nothing in common. Exception to this two-side space is the Mobius ring, as we show here. However, as we know, if the distance is small enough, then the two segments can have only one point in common. So that means in a Mobius ring, we can still define locally two-sided region. So our Mobius ring, locally it can be two-sided, while globally it's non-two-sided, as we can also show here. Now, if a point C is outside a straight line AB, we can say there must exist another point D on the other side of AB, which satisfies that the point C and D is an intersection between the circle A and circle B, and it constructs a two-sided two-dimensional space. Here, we use circle because unlike straight line, which is the same in all dimensions, a round object has different embedment in different dimensions. For example, a circle in two-dimensional space and a ball in three-dimensional space. So, by observing how two circles intersect each other, we can define two-dimensional space. This picture actually defines a lot of geometry objects, such as a triangle and an angle. Here, we are looking at the angle and how to measure it. For the angle BAC shown here, right? How to measure it? We use an angle measure distance called U to construct a circle at the vertex A, which intersect the two arms at C and B. Then we define the angle distance ratio as the distance BC squared divided by 4U squared. We can see in this graph, it increases with the increased angle. In fact, the angle distance ratio is in the range between 0 and 1. 0 means for a ray, and 1 means for a straight line. Now, let's talk about all right angles are equal to each other. Before that, we need to define what is a right angle. We will use tangent and perpendicular relation. Assuming there is a point C outside straight line AB. If on the straight line AB, there exists 3 points D prime, E, and F, which satisfy 2D CD prime is less than D prime E and D prime F, with EF on the two sides of the straight line CD, then we will find easily CD prime is less than both CE and CF. With this condition, we can prove, centered from C, there is only one circle which intersects with straight line AB with 1 point only. We call it D, and we define this relation as C is tangent with straight line AB at point D. There are some exceptions to this rule in non-Euclidean space. For example, if you look at the spherical surface, assuming we look at the relation between the North Pole and the equator, we know that from North Pole to equator, the distance is always the same, and you cannot find that 3 points D prime, E, and F has that relation. Another thing here is, as we show in this picture, there is a monotonic relation between the distance CE and DE. And finally, if a straight line segment cross one circle, it will cross at 1 point, such as segment AD cross at E. We can ask this question another way. Suppose we have a straight line CE. The question is, from E, how many straight lines were tangent with C at point D? The answer is only 1. We can also define the perpendicular relation. If we make another circle inside the C the center is on the segment CD, and it intersects the circle C at point D, then this circle will have only one intersection with straight line AB. So in other words, if D is a tangent point of C to AB, then every point on straight line CD is a tangent D is a tangent point to every point on straight line CD to AB, and this relation is mutual. So that's finally come to the two-dimensional. In the two-dimensional space, from every point D, you can only construct two mutually perpendicular straight lines. Finally, we can address all right angles are equal to each other. We can create right angle by perpendicular relations and define the angle distance ratio for a right angle as right ratio. The Euclidean geometry just says all right ratios are 1/2. Here, let's assume OA, OB, OC, and OD are all 1. Because all right ratios are 1/2, AC, CB, BD, and DA are all square root 2. And because AB is 2 and CD is 2, so the angle distance ratio for angle CAD is also a right angle. So, which is true for CAD, ACB, CBD, DAC. So essentially, what we're creating is something called a square. If we stack two squares side by side like this, and we know ADC is a right angle, CDE is also a right angle, then ADE is a straight line segment. Essentially, what we're creating here is a rectangular with a side ratio 1:2. If we can create a rectangular of any shape, then we can prove the parallel postulation. In other words, the reason we have parallel postulation as an independent axiom is because we do not understand all right angles are equal to each other. If we stack the identical squares in 2 dimensions, we can create a measuring grid as shown here. For example, we use measuring grid to measure 3 triangles. Because of this, the Euclidean space is homogeneous, it's isometric, and also the measuring grid has only 2 parameters. One is the orientation, the other one is the size of each square. So that means the Euclidean space is isotropic, reflective, and similar. We can compare it with a spherical surface. You can also apply spherical surface with triangle or other identical polygon, but only for select size. So a spherical surface is orthogonal, except it is not similar. Now we can talk about geometric object in Euclidean space. So let's refine our constructive object as a repeatable object. So if the constructive object is determined by the first rule of starting point and starting rate as shown here, then define the rest rule which reference each other and the starting point and starting rate. Here we first contract the first rule rate, then put a length on the rate, then construct a triangle by knowing the length of the other 2 sides. And we can have a concept called property, which is a true statement of a geometric object. For a repeated object, it starts from a starting point. So it is a position-related property, and which can be reconciled by a translation. And for the starting ray, it has an orientation. So it's an orientation-related property, which can be reconciled by a rotation. And on which side of the starting point you construct the object, you basically can actually construct either a repeated object or reflective object, as you can see here, if you do it on the other side. And also, if you construct this object by scaling down or scaling up all the distance by a constant, then you can still construct it. Because all angles are the ratio of the distance, so when you construct by scale the distance, or the angle will not change. Right. So essentially, you can also have other properties, right? But essentially, for a repeated object, how you construct it determines the property. Namely, if you construct the object on the same side using the same scale, you will say that the side-related property will be same, and distance-related property would be exactly the same. On the other hand, if you construct the object on the different side with different scale, you say the distance-related property is related by the scale, but the ratio related is still the same. Having a constant right ratio of 1/2 is not end of the story. As we know, flatness is a special case of smoothness, so we need to study the smoothness in more details. Here is a conical surface we have shown before, which has a tip at A. We can construct this conical surface by cutting along CAC' from a Euclidean surface and stick along the CAC' to create the segment AC on the conical surface as shown here. The angle of CAC' is called cut angle. The bigger the cut angle, the sharper the tip at A. We can also measure the right ratio at the point F with two arms FB and FC, as shown here. So BC essentially the distance to measure the right ratio at F. As we can see here, the arm FC continues as a C'H here. So the right ratio is 1/2 before the segment BC and is less than 1/2 after the segment BC. So there is a decrease from the constant right ratio as shown here. The angle AFB is called measuring angle in this problem. So we are interested in when the transition happens and how fast the transition happens. So we define the transition distance as FB here. Here we normalize the FB with the distance FA. Right. Another thing we can measure is the first derivative of the right ratio to the measuring distance at the transition as shown right. So in the lab, we see the normalized transition distance. We can see it decreases greatest at 45 degrees. On the left, we see when the cutting angle increases, the transitional, the first derivative also decreases, but it still decreases fastest along the 45 degrees. So we can define the bisect of the right angle as the distance, as the bisect of the right angle as the direction of it. Here's something interesting. If A is between the two arms FB and FC, we see this kind of transition, namely the right ratio is 1/2, then decrease from 1/2. But A is not within this arm, within these two arms. The right ratio is always 1/2. So if we measure the right ratio on a surface, we'll see a sudden drop of the right ratio when the angle changes. So one way to define the smoothness of the surface is if we say the right ratios are smooth in the mathematical term on a surface. That would avoid such a singular point of non-smoothness. Another interesting point is if we define the local right ratio as a right ratio when the measuring distance approaches 0, and then we calculate the first derivative, we will find that the first derivative of local right ratio are always 0 until the point is at or near the transition, near the tip of the conical surface. So we can use the first derivative of local right ratio to pinpoint where the surface is not smooth. Now we can talk about curvature. Before talk about curvature, we should talk about flatness, which means there's no curvature. We can define flat as constant right ratio. So we know the Euclidean space has a constant flat ratio of 1/2. Is it only a special case of flatness? We can prove that if a smooth surface is flat at one point, not only the angle distance ratio has to be 1/2, but also the surface has to be Euclidean. So the Euclidean surface is unique because it's the only flat surface. Now we can calculate curvature for some non-flat surface like torus. Basically, it's a donut shape. We'll calculate the angle distance ratio for right ratio for different angle measuring distance as shown here. Here we are calculating the point at the very outside of this torus and the point at the very inside of this torus. We can see they have a different trend. For the outside is the gray curve below, and the inside is a black curve above, because they have different way of curved. Right. And we can look at in more details by looking at the derivative of the local right ratios. We can first see that the first derivative is 0. If you look at the angle measuring distance at 0, and because of that, the angle distance ratio is 1/2 as shown here. The second derivative just tells us how the surface is curved. So let's summarize the new axiom set for Euclidean geometry. It is a quantification and enhancement of Euclidean axiom set. It says stability. The first one says stability by abstraction of geometry object. The second says measurable by distance. Third continuous by straight line segments. The fourth says boundless and smooth by extending straight line segments. The fifth says two-dimensional and two-sided. The sixth says right ratio are always 1/2. Except 1 and 5, they are the original 4 axioms of the Euclidean original one, just in different order. What's the improvement? The first one, this axiom set is progressive, meaning our statement has different scope, right? And it's narrowed down the space step by step, right? Only the last one says it is Euclidean. And if you have 1, 2, 3, 4, 5, you can apply to any surface other than any two-sided surface, right? The second one is, as you can see, we introduce no new concept in any of the axioms. And because that, it's complete and simpler, at least more complete than the original Euclidean geometry that introduced two new axioms, and much simpler than the standard answer. And also, the important thing here is we do no longer require congruence. The congruence comes as axiom 6. And also, it introduced a local right ratio as a new tool to study non-Euclidean geometry, namely smoothness and the local, if it's smooth, then it's a local Euclidean, and how to measure the curvature. Acknowledgement. First, I will thank my middle school geometry teacher, Mr. Liu, and two of my professors from college, and my PhD advisor, Dr. Paul Hall. All of them encouraged me to do critical thinking and to do alternative thinking. And also, I'd like to thank Mr. Victor Agile, one of my readers, who find a fatal mistake in my original approach. Please read my paper and try to find problem in it. Please distribute our paper. It's a paper between me and my daughter Alice. Please do invent wheels in your lives.